In the previous lecture, we were talking about Fourier series, coefficients, AK, and we were specifically looking at finding out the Fourier series coefficients or Fourier coefficients A sub k for a pulse train. So this is a pulse train. And why am I calling it a pulse train? Simply because it is a train of pulses. So you have pulse 1, 2, 3, and so on, and it is one after the other after the other. So it is a continuous train, as different cars in a train. You have pulses that are coming after the other. So it's a periodic pulse train. All right. So let's revisit this example, and then we can move on to other things. So in order to find the Fourier series coefficients of x of t, we called those Fourier series coefficients as a sub k, and we looked at this particular pulse train, which had a time period of 4, right? Time period was 4, and you can look at one time period as -2 to 2, or from -1 to 3, or from 0 to 4. But the goal is to find the Fourier series coefficients based on a particular formula that we derived in the previous class. And that derivation was based off of the fact that we can take an orthogonal set of exponential functions and we can project any periodic signal onto each of those uh, functions in the orthogonal set, which in this case specifically is the exponential complex exponentials, and then we sum up all those projections to get back our x of t. And we were able to do this as an approximation, not an exact representation of x of t. The first step, find the time period. This time period was 4 based on how this graph is sketched, which means that the fundamental radiant frequency omega naught is pi over 2. Then we move on to finding out the average value of the signal. Half the time it is on, half the time it is off. When it is on, it is 1. When it is off, it is 0. So the average value should be half. That is a very straightforward way of coming to the same conclusion as saying a sub 0 is 1 over t integration over one time period x of t dt. So if you plug in for t as -2 to 2 or -1 to 3 or 0 to 4, no matter what you do, you will get 1 over 4 integration over one time period to evaluate to half. Recommendation here, when the signal itself, the periodic signal itself is symmetric, even symmetry, then choose the time period such that it is going from -2 to 2 or negative t over 2 to t over 2 in a very symmetric fashion. That will help you to work out the math in a much easier manner. We will take a few, we will take a look at some examples in which we will change those limits. Instead of looking at -2 to 2, we will take a look at 0 to 4 and see what are the consequences in terms of the messiness in the math. We used these Euler identities to help with the simplification, and at this point you will be expected to know them. All right, so first we found out a sub 0, then we went on to a sub k. These are the other exponential Fourier series coefficients, or simply those are the Fourier series coefficients, FS coefficients. I like to denote Fourier series coefficients as a sub k or b sub k or c sub k for different signals. In some textbooks you might see c sub n also for Fourier series coefficients. I'm just using a sub k because I like to use that terminology. K is the index, right? So when k is 0, we are talking about the DC term. When k is 1, we are talking about the fundamental frequency. When k is 2, we are talking about the second harmonic, and so on. So a sub k in general is 1 over t integration over one time period x of t e to the negative j k omega naught t dt. Projecting x of t onto each of those orthogonal complex exponentials to find out their coefficients. The AK is essentially the magnitude of that projection. So evaluate that with respect to x of t is a square wave. So this comes down to -2 to 2 as the integration of the limits. X of t is 1 over there. Now between -2 and -1 it is 0. So this even simplifies down to -1 to 1. You integrate the complex exponential, which should be straightforward, plug in the limits, simplify, and at the end you express the result as a sinc function, which is essentially sine x over x. So the goal is separate out when k is 0 and separate out k not equal to 0. In some cases, both might be included. So k might be included in this general form. In some other cases, it might not be the case. So, it's recommended, it is important actually to evaluate k equals 0 first and then go into k not equal to 0 case. So you would write ak as this for, let's see, x of t Fourier series coefficients. Now, there is another way of looking at the same expression here, which is I can write x of t by evaluating. So if you see this expression here, where is it? Right here. X of t, right here. So what I'm going to do is I'm going to copy this from here and paste it right here so that you see how we can write x of t. We can write x of t as this particular summation. So if I break this down into the two cases that I have for the bracket notation, I can say x of t is half, that is when k equals 0, plus summation k equals -infinity to infinity and k is not equal to 0, ak, which in this case is half sinc k pi over 2 e to the negative j k omega naught, well, omega naught also we know, right, pi over 2. So we have essentially expressed x of t as a summation here. Now, one problem here is it is not equal, it is an approximation. So I'm going to be using the approximation sign here. That is how we represent a periodic signal, in this case a pulse train, using the Fourier series coefficients. The Fourier series coefficients are right here, ak. And half that corresponds to that. All right, let's move on. We looked at the sinc function in its two forms. The one on the left is sine x over x, which is the one that we are going to use in this class. But there is also another commonly used form, which is sine pi x over pi x, which MATLAB uses. And the difference is the zero crossings in each of these functions. The zero crossings for sine x over x with respect to x happen at pi, 2 pi, 3 pi, pi, -2 pi, and so on. So integer multiples of pi. And for sine pi x over pi x, they happen at integers, plus and minus 1, plus and minus 2, apart from 0, plus and minus 1, plus and minus 2, plus and minus 3, and so on. So that's the only difference. So, but for this class, we are using sine x over x. But that is something to note. Next, we looked at the first 6 harmonics of the pulse train and we laid them out. We said, okay, if this is the k on the left column, which is the index corresponding to the kth harmonic, and on the right we have ak, which is half sinc k pi over 2, When it was 0, it was half. When it was 1, 2, 3, 4, all of that, we noticed that all the even harmonics went to 0 and all the odd harmonics will have some finite value. We can use this information to start a sketch, and the sketch will look like this. And the x-axis over here is k, the y-axis over here is ak. Now, can you do this as an experiment? I recommend you to do this. Use your phone to generate a square wave. How can you use a phone to generate a square wave? There will be wave generator apps that will generate different functions, and they will generate a sound for those particular functions. You might have a triangle, sawtooth, sinusoidal, DC, square wave in this case. So you can use your phone to generate that sound, and you can pick up some frequency, say 1 kilohertz square wave. Then there are many web-based spectrum analyzers. And I can post a note on Piazza giving you some links there for a web-based spectrum analyzer. When you play this on your phone, have your microphone on your computer on, so that the web-based spectrum analyzer is essentially showing you all the frequencies that are present in that square wave that you generated on your phone. The result will be something like this. It will be showing you a sync kind of shape with specific harmonics, the odd harmonics at 1, -1, -3, 3, and so on. So you can visualize it a little bit better if you do this sort of a quick experiment using your phone and a computer with a web-based spectrum analyzer. You can obviously, if you have taken circuits, or if you have taken any class related to analog discovery, you can also do this in waveforms. So you can generate a square wave using a function generator, arbitrary waveform generator in waveforms software, and you can hook it up to a channel which you can measure, look at the spectrum for, which is also part of waveforms. So you can do this experiment very quickly. If you don't have access to an analog discovery board or waveform software, you can quickly do this with your phone and a computer. If you're interested, let me know and I can provide you more resources or help whatever you need with this. All right. So one thing to note here, this is a sync shape envelope, and the DC term is the highest in terms of its strength, and as you go away from the DC term, the magnitude of that harmonic goes smaller and smaller. All the even harmonics are 0, all the odd harmonics are going down in their magnitude. And one thing to note over here is, because x of t, the signal, the pulse train, was real and even, its Fourier series coefficients also turned out to be real and even. This is a symmetry property of Fourier series that we will be proving later on. Now, if k is related to the frequency, right? K is related to frequency because we are saying this is 0, this is at 1 omega naught, this is at 2 omega naught, this is at 3 omega naught. In our example, when we said f is frequency is 1 kilohertz, that was the fundamental, which means omega naught would have been 2 pi kilohertz, kiloradians per second. So the frequencies would be present at what? Omega naught, 2 omega naught, 0, negative omega naught, and so on. If you take the square wave and you move it up and down, will the omega naught terms change, or 2 omega naught terms change, or 3 omega naught terms change? What I mean by that is this. Let's see. If I add another slide here, imagine this is here, this is here, this is here, some pulse train. Now, if you move this up and down vertically, will the Fourier series coefficients change? That is the question. Because the Fourier series coefficients, those are related to the frequencies in that square wave, right? The frequencies of all the sinusoids, when you add them up, you get the square wave. So will the AK change if you keep moving this up and down? You know, imagine this to be moving up and down like that. Will it change? No is correct. No is mostly correct. How about A0? A0 is the DC value, right? The no frequency value will, yes, but actually no, yes. So A0 will change when you change this, but AK except for A0 will not change. So only the DC term will change as you move this periodic wave up and down vertically. So when you do a vertical shift of a periodic signal, only the DC term will change. Everything else will remain as is. This can be summarized as this particular note. When x of t, the periodic signal, is vertically shifted by some constant c, it might be positive, it might be negative, whatever the case. If it is shifted vertically by c, only A0, the DC term, will change, and it will change to A0 plus c. That's it. So in our case, when we had this, let's see, when we had this particular answer for the square wave, if you add c to this by changing the DC value of the pulse train, you literally add c to this. AC plus A sub 0 plus c. That's it. Everything else remains as is. That is essentially captured over here. I should just highlight C here. Everything else remains as is. This just does not apply for the pulse train. It applies for any periodic signal. When you move it up and down, only the DC component, A sub 0, changes. All the other harmonics remain as is. We have also noted this. A sub k is the same as A sub minus k. A1 was the same as A sub minus 1. A3 was same as A sub minus 3. A2 was the same as A sub minus 2. For this, so we got even coefficients for an even signal. Let's move on here. We are continuing with the same pulse train example. At the top, we have x of t represented as this pulse train with the same time period 4, same Fourier series coefficients a sub k, which is a sub 0 is half, a sub k is uh, half sinc k pi over 2. This is what we call a reference result. So this is a reference result for pulse trains. So you can use this to solve Fourier series coefficients for other periodic signals that are related to x of t. All right, let's look at this. Let's consider the first 6 harmonics. We have x of t over here written as a summation. In this case, we are only looking at the first 6 harmonics, so we are going from -6 to 6, and this is an approximation, so we used an approximation sign, ak e to the jk pi over 2t. We know that we can express x of t as a summation of in this form. That's our exponential Fourier series. Now you expand this into 1, 2, 3, 4, 5, 6, 7 terms, one of them for a sub 0, the other 6 for all the odd components, all the odd harmonics. All the even harmonics turned out to be 0 because of sinc function evaluating to 0 at those k's. So you only got 7 components here. Now what you can do is this. In order for you to simplify, you can do this. Leave A0 as is. Then you start combining the terms with like powers of the exponent. These two guys have e to the negative 5 pi over 2 and e to the plus j 5 pi over 2t. So you can combine those. Next, you can combine these two guys, this and this. And the last one, maybe I can draw it in a slightly different color. This guy and this guy. We are trying to combine the terms in which the power in the complex exponential is consistent so that we can use Euler's identities to simplify further. So a sub 0 remains as is, which is half. We know that from here, from the reference result. Then we also know that the a sub k's from the table we looked at. So a sub negative 5 and 5 was 1 over 5 pi. So we pulled that out as a common factor. And then we have the exponentials, the complex exponentials in the parentheses here, here, and here. So let me highlight them based on the color choice that I chose. There, blue there, and green there. Now, using Euler's identities, we can express that as cosine x is e to the jx plus e to the minus jx divided by 2. So I'm essentially using that. And for the next one, I have this. And for the next one, I have green. So we have essentially written x of t in many different forms. One was we started off with a pulse train. So we could write x of t in bracket notation. 1 from this time to this time and 0 from this time to this time, periodic. Then we express x of t in the form of exponential Fourier series by evaluating AKs. Then we transitioned into trigonometric functions. So we are evaluating now x of t. We are writing x of t as a sum of sinusoids. Oh yeah, you're right. The middle one is blue. Oops. Yes. and then this guy remains as is, right? So what we can do now is, because we have these very nice cosines, we can you know, type it up into a MATLAB program and try to sketch them and see what they look like. So this is kind of what we were doing the last time. The blue guy is x of t and the red one is an approximation of x of t while considering only the first 6 harmonics. So when you consider the first 6 harmonics, you know that all the even harmonics are 0, all the odd harmonics are evaluating to some values, a plus and minus 1, plus and minus 3, plus and minus 5, those have some values in them. So if you write up a MATLAB code in which you define the function x as half for some time, and then 2 divided by pi cosine pi over 2t for some other time, and then x3 and x5, and then add those up. And essentially that's what we are sketching over here. You see what happens. You are going closer and closer to the square wave. In fact, if you add up all the harmonics from negative infinity to infinity, as you are taking k to infinity, the red graph is going to look more and more like the blue one. So it depends on the number of terms that you have in your Fourier series that will make it a much better approximation. So this code is there and I will make it available, of course, so you can play with it in MATLAB to see what happens if you add more terms to this, whether it gets closer and closer or not. Now, to go one level deeper, on this graph, we are showing the effects of magnitudes of individual harmonics. So the DC term is a sub 0, which is half, so that's a red straight line. Then you have the yellow dashed line for the fundamental frequency. The amplitude of the fundamental frequency was a sub 1. So a sub 1, which is the same as a sub minus 1, I believe was 1 over pi. So we are essentially evaluating 1 over pi here in the yellow one. Then you have the third harmonic, the fifth harmonic. Those are amplitudes of the sinusoids that make up the square wave. All of them individually are plotted over here. So essentially I'm plotting x, what is that? Did I say? Okay, so the amplitude here, 2 divided by 3 pi, 2 divided by pi, and so on. For x1, x3, x5. So those are essentially your showing you the effects of the individual harmonics. Let us make it into a result, a reference result that we are going to use from here on out for a generic pulse train. General pulse train. So for a general pulse train, and we talked about why pulse train, right? A train of pulses. Let us say that the pulse train is on between negative t1 and t1, and the time period for that pulse train is capital T. It is symmetric, so it has even symmetry. You can denote all this information by simply writing pulse, and inside the parentheses you write t sub 1 comma t. T sub 1 indicates the time for which it is on, t indicates the time period of the pulse train. Now to find the Fourier series coefficients a sub k for this general pulse train, we will follow the same procedure. First, find the time period. Well, time period is t. What is omega naught? 2 pi divided by t. What is a sub 0? Integrate over one time period and then divided by the time period. So integration will be from negative t1 to t1. Let me see, negative t1 to t1, and you divide it by 1 over t. That gives you the average over one time period. So that t is because of that t there. Simplify to get 2t1 divided by t for a sub 0. Next, we evaluate a sub k other than 0. So that will be in general 1 over t integration over one time period x of t e to the negative jk omega naught t. That's the general result. Now it is periodic, so it helps me a lot to choose the time period between negative t over 2 to t over 2. In fact, some of it is 0, so I only need to integrate between negative t1 and t1. 1 over t remains as is, and inside the integration I have 1 for x of t, and I also have e to the negative jk omega naught t for e to the negative jk omega naught t. That's my orthogonal set, the functions in the orthogonal set. Because I know that I can integrate this, I will get another complex exponential. I will get divide by negative jk omega naught as well, which I can use to simplify and write that result in the sinc form. So the general result is 2t1 divided by t sinc k omega naught t1 for k not equal to 0. For k equals to 0, it is going to be 2t1 divided by t using L'Hopital rule. So this is also part of this, which means I can write one standard result for Fourier series coefficients for a general pulse train, which is 2t1 divided by t sinc k omega naught t1 for all k. Now in the previous example, our capital T was 4, omega naught was pi divided by 2. So if you plug those into here, you will see that, T1 was what? I believe T1 was negative 1 to 1. So 1. So if you plug those numbers in, you will see that this will satisfy the previous answer. So that's a result that you are going to use multiple times. Also, you can write up x of t as a summation of those coefficients multiplied by their harmonics. So 2t1 divided by t, that is the a sub 0 term. Summation k equals negative infinity to infinity. 2t1 divided by t sinc k omega naught t1 multiplied by e to the plus j k omega naught t. That is also one way you can write x of t. So this is expressing x of t in terms of its Fourier series coefficients. This is expressing the Fourier series coefficients themselves for a general pulse train. All right, questions about this example? All right. Next, what we can do is this. I already evaluated that pulse train. Yeah. Okay. In the next step, we will try to solve the same problem, but we will change the time period. Instead of going from negative 2 to 2, which was recommended for even signals, we will go from 0 to 4. So Adrian says, what if the amplitude is not 1? So let's make this m. Everything will be m, right? So it will be, everything will be multiplied by m. All right, let's see. Okay. what do we have here? Right, 0 to 4. So when you are integrating from 0 to 4, it should give you the same answer, but let's just verify that quickly. So we are evaluating the same Fourier series coefficients for the same pulse train. It was on between -1 and 1. It was, the time period was getting evaluated for 4 seconds. We are right now focusing on 0 to 4. 1 over 4 because time period is 4. X of t is 1 during that time, well, part of the time, which is from 0 to 1. E to the negative j k omega naught t. So 0 to 4 can be broken down into 0 to 1, and then 1 to 2, 1 to 3, in fact it is off, and then 3 to 4. So over here it is on, here it is on, from 1 to 3 it is off. So we got only two pieces here. The first one where the integration goes from 0 to 1 and x of t is 1 there. And the other integration is from 3 to 4 when the also x of t is 1 there. At times between 1 and 3, x of t is 0. So you integrate, you simplify, you get this. Now, as you can see, this is not the exact same form as half sinc k pi over 2. So we are going to have to, manipulate this using some factorization skills. And we can do it in two different approaches. Approach 1 is to factor e to the minus jk pi. If you factor e to the minus jk pi from e to the minus jk 3 pi over 2, which is that term there, you can rewrite this inside the square bracket, e to the minus jk pi over 2 minus e to the minus jk 3 pi over 2 as e to the minus jk pi over 2, same as this. Let me use there and there. And after that, I'm writing e to the minus jk pi and e to the plus jk pi to be able to factor things out later. Minus remains as is, and then you are writing e to the minus jk pi multiplied by e to the minus jk pi again, because we are doing the factorization that way. Next, you pull out the common term. What is the common term here? The common term is e to the minus jk pi. So if you pull that out, and you will be left with e to the plus jk pi over 2 from, let's see here. This is being written as that, minus plus is there, factor out e to the minus jk pi, 1 over 4. So all of this, actually all of this remains as is. You have factored out this term and this term as this term. What is left inside is the product of these two guys, which is that, and this, which is that. All of this so that it comes into a form where you can use Euler's identity. E to the plus jx minus e to the minus jx. I think I can write that as 2j sine x. So if you have 2j sine x for this, let me write that down in red. For this, you can write this as 2j sine k pi over 2. J cancels out. This 2 cancels with that guy. And now what you have is, you have a generic result, which is this guy. But before we do that, I want you to note what this is. What is that? Let me do these on a different page of e to the minus jk pi. Okay, so let's do it over here. E to the minus jk pi equals e to the minus j pi raised to k. equals -1 k. You guys agree with that? So when you're doing e to the minus j pi, you are essentially evaluating, right? This is real, this is imaginary. So when you have a phase term of negative pi or plus pi, you will have -1. How about this? How about e to the j pi over 2 k? What would that be? Actually, I can write plus -1 here, plus -1 here, plus -1 here. Oh, actually, no, not plus -1, just -1. All right, guys, the question is e to the j pi over 2k. What is it? Right. J raised to k. Similarly, what is that? Because it is over here and here. The top one is for e j pi over 2k, or e raised to j pi over 2, and then the second one is e to the minus j pi over 2. So by using the knowledge of our complex numbers, we can quickly write these things. But we are using the first one for now. E to the j k pi is -1 raised to k. That's what we are using here. So we simplify and we will be able to write this as this term here. Negative of -1 raised to k half sinc k pi over 2 when k is not equal to 0. And as you can see, this is not exactly the same as half sinc k pi over 2, but when you actually evaluate all the AKs, they will evaluate to be the same as before. So it is, in theory, it is the same as half sinc k pi over 2. They don't look the same, but they evaluate to be the same. Next, can I do an approach 2 where I deal with that AK slightly differently? Over here you can see that the powers are different because we chose the time period from 0 to 4 instead of -2 to 2. Over here we are choosing to factor out something different. We are choosing to factor out e to the negative jk 3 pi over 2. We are writing e to the minus j and plus jk pi over 2 as is, so that is just simply 1. We have factored out -1 as well, so the second term is coming up front, and then this is as is. -1/4 -1 divided by negative j pi over 2 remains as is. Inside over here you can combine the two negative powers here, so e to the negative jk 4 pi over 2 multiplied by e to the jk pi over 2 minus e to the minus jk pi over 2 as is. What is this guy going to be? Let me use a different color. Green. This is going to be simply e to the negative 2j, sorry, let me say negative j 2 pi raised to k, which is 1. So all of that is simply 1. and you have e to the jk pi over 2 here, e to the minus jk pi over 2 here. Now you can use the identity, Euler's identity, to write it in this form. Things will cancel out and you will be able to write half sinc k pi over 2 for all k. So the summary of this discussion is you can get many different forms for the same answer depending on how your interval is chosen t. In general, my recommendation is choose negative t over 2 to t over 2. If your signal x of t is symmetric, choose a symmetric interval for that time period. This is a symmetry property that we'll prove on later, which is x of t is even. The Fourier series coefficients turn out to be even. And in fact, if x of t was real and even, your Fourier series coefficients would be real and even. We will prove this later on. Okay, let's move on here. So it's 12 o'clock right now. What I'll do is this. I will stop here. There's no point going